Welcome to this lecture series in number theory. In this lecture, we'll prove Wilson's theorem, which is one of the earliest results in this subject. And we will also look at some applications. Let's recall some of the things that we need. So we will need the notion of the inverse of an integer modulo another integer. So if a is a given integer and n is another integer, then b is called an inverse of a modulo n if this congruence holds. But we also saw that any such thing is unique up to remainders, meaning if b and b prime are two different inverses of a modulo n, then they will be congruent modulo n. So modulo n, any two inverses are same, so you might say the inverse rather than an inverse. Okay, and just a corollary of that remark is that if a is invertible modulo n, and not everything is, the criterion for something to be invertible modulo n is precisely the relative primality of the given number. So if a is invertible modulo n, which is to say that if a is relatively prime to n, then a has a unique inverse in this range. I could have also written a 0 here, but since 0 is not invertible, so it doesn't matter. It's still, what I've written is fine. So if a is invertible modulo n, then there is a unique inverse in this set. That's okay. And we will also probably use the fundamental theorem of arithmetic at one point here. And we will use the various properties of GCD, this, that, everything I cannot recall. I don't want to recall. So with that, let us proceed. Some problems for practice. This is a very simple problem. Not much of number theory is needed here, but still some thinking is required. This is a very nice set of guided exercises. The last one, I have used the notion of a limit, which is something that one reads either in high school calculus or in undergrad courses in real analysis. But I have explicitly written down what that means. So do not get scared away from this symbol if you haven't seen it before. Okay. So let's look at a phenomenon for a particular prime, which we will prove in general, and that general statement is Wilson's theorem. Okay. So we have this prime 11, and what are all the possible remainders that you get when you divide something by it? It's a set of 11 numbers. It's this set. But how many of these are invertible modulo p? Well, p is a prime, so the only things which are not invertible modulo p are those which are divisible by p. In general, the things which are not invertible modulo n are those which have some non-trivial common factor with n, which are not relatively prime to n. But if p is a prime, then and suppose let's say some number a is not relatively prime to p, which is to say that it is not invertible modulo p, then p must divide it. As soon as they share a common factor, the common factor should be p. That's immediate by the definition of a prime. Whatever, so 0 is not invertible modulo p, but everything else is. So let me drop that from our list. I'm not concerned with 0 here. We are only concerned with things which are invertible modulo p, and I have mentioned them in this circular order. These are all the possible remainders which are invertible modulo p. No other remainder, the only other remainder is 0, because together with 0, this is all the possible remainders. 0 is not invertible modulo p, and all of the things listed here are. Fine, great. Now let us pair up the inverses. So let's start with 1. 1 is its own inverse. We will be marking out the inverse within them. As we mentioned in the recall, every integer has every invertible integer. You fix an integer a, and if it is invertible modulo p, it will have a unique inverse in this range. So when I say inverse, I mean inverse in this range. Okay. So what is the inverse of 1? It's 1 itself, because 1 times 1 is congruent to 1 modulo p. So the inverse of 1 is 1. I'll make a circular loop here. I will explain why this circular loop comes about. I'll explain what I mean by this circular loop in a moment. What about 2? What is the inverse of 2? Well, 2 has 6 as its inverse, because 2 times 6 is 12, which leaves a remainder of 1 modulo 11. What about 3? 3 has 4 as its inverse. 5, 5, I don't know. What about 5? 5 has 9 as its inverse, because 45 leaves a remainder of 1 modulo 11. What about 7? 7 has 8 as its inverse. And finally, what about 10? 10 is its own inverse. So the circular loop was just trying to show that something is its own inverse. We have connected an inverse with itself. Inverses come in pairs. If 6 is the inverse of 2, then 2 is the inverse of 6, clearly. So we are just recording via these edges, as they are called. These lines are called, and these loops are called edges. Via these edges, we are just recording the inverses of every remainder. Okay? So what happens if we multiply all these numbers? What happens if we multiply all these numbers? Well, these will, modulo p, these will kill each other. So what I'm trying to say is, suppose I try to calculate this product. 1 times 2 times 3, 4, so on, which is 10 factorial. So this is, I will write it like this. I will write it as 1 into 10, and then the rest, which I will write like this. I will group 2 and 6 together, and then 3 and 4 together, 5 and 9 together, 7 and 8 together. Right? This is how we will group. So all we are doing is 1 and 10 are somewhat special. They are in their own club. But everything else we have paired up with its unique inverse. Right? But this is congruent to 1 mod 11. This is congruent to 1 mod 11. This is congruent to 1 mod 11. And this is also congruent to 1 mod 11. So what we get is, the whole thing is congruent to 10 mod 11. Right? Because all of these are basically gone. But 10 is congruent to minus 1 mod 11. So I might also write this as follows. Right. So we are seeing that 10 factorial is congruent to minus 1 modulo 11. And one can make the general statement, which is Wilson's theorem, that is p is a prime. Then p minus 1 factorial is congruent to minus 1 modulo 11. Modulo p. So this is what we are going to do. I hope the idea is clear from just this very simple example. The idea is here, pairing up with inverses. Inverses come in pairs, you pair up, and blah. Okay. So before we prove the general statement, we need to get rid of this one simple fact. Suppose p is a prime and x is some integer. Then x is its own inverse modulo p if and only if x is either congruent to, what have I written? Either congruent to minus 1 or 1 modulo p. 1 or minus 1 modulo p. If x is congruent to 1 modulo p, clearly x is its own inverse. If x is congruent to minus 1 modulo p, clearly x is its own inverse. So one direction is clear. We will prove the other direction. So prove, suppose x is its own inverse modulo p, then by definition, x times x is congruent to 1 modulo p, which implies x square is congruent to 1 modulo p, which implies x square minus 1 is congruent to 0 modulo p, which implies p divides x square minus 1, which implies p divides this product. Right? But p is a prime, and as we know, if a prime divides the product of two integers, it divides at least one of them. So p either divides this or that, well, or both. But if p divides this, we have x congruent to 1 modulo p. If p divides that, we have x congruent to minus 1 modulo p, and we are done. So very simple. right? So what this shows is that amongst all these numbers, 1, 2, dot, 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 up to p minus 1, the only numbers which are their own inverses are 1 and p minus 1, and every other number will pair up with someone else. And the reasoning that we showed in the previous page will go through. So Wilson's theorem says, this is due to Wilson, let me write. This was discovered by Wilson, but it was proven by Gauss. But still it is called Wilson's theorem. So let p be a prime. We want to show that p minus 1 factorial is congruent to minus 1 modulo p. So it's the same reasoning that we saw earlier. We can partition this set 2 up to p minus 2 p minus 2 up to p minus 2 into sets of size 2 each, where every set consists of mutual inverses. So I'm not writing a very detailed proof here. What I'm trying to say is, just like we saw in the previous page, you partition this set into doubletons. Doubletons meaning sets of size 2, where every such set consists of mutual inverses modulo p, meaning that b is the inverse of a, and naturally then a is the inverse of b. So the product that we have, that we are concerned with, p minus 1 factorial, would then be 1 times p minus 1. This we isolate separately, times the rest, which is 2 into 3 into blah blah blah. But the point is that this is congruent to 1 modulo p, because the inverses come in pair and they kill each other modulo p. Kill each other meaning, well, I shouldn't say kill each other, I must say they make themselves disappear, so to say. So this is congruent to p minus 1 modulo p, which is same as minus 1 modulo p. So here I could write a very detailed explanation, all the symbols, etc., but I don't see any point to it. I think this should be sufficient. So this is Wilson's theorem. Great. So here is the converse of Wilson's theorem. We just saw that if p is a prime, then p minus 1 factorial is congruent to minus 1 modulo p. Here we are showing that, in fact, we are showing something stronger, but in particular what we are going to show is that if n is not prime, then this congruence cannot happen, meaning n minus 1 factorial is not congruent to minus 1. Therefore, Wilson's theorem characterizes primes. Primes are precisely those natural numbers which are at least 2 and which satisfy this congruence. Okay, so the stronger statement that we are proving is that if n is composite, then it divides n minus 1 factorial. Not obvious. Okay, so you can think about it. It's not very difficult. Alright, so there could be many proofs of it. In fact, there are many proofs of it. But let me give a proof using the sieve of Eratosthenes. So, suppose, well, since n is composite, we know that there is a prime divisor, there is a prime p such that p is at most square root of n and p divides n. Right? So we will make two cases now. The first case is that p is strictly less than root n. In this case, note that we have n is p times n by p. That's how we will write it. Both are integers. P divides n, so this is also an integer. So we have just written n as the product of two integers. The point is, they are different. P and n by p are different. Because if they were the same, if this was an equality, then this strictly less than wouldn't happen. It would actually be an equality here also. So this is a fact, and both are less than n minus 1. I mean, both are less than equal to n minus 1. So what I'm saying is the inequality is there and both are less than equal to n minus 1. Now I might run into some trouble if n is too small. So let's see, if n is 4, is it fine? If n is 4, then well, I cannot even land in this case. So it's fine, I think. What about n is equal to 6? If n is 6, then yeah, I think this is fine. If at all there is some problem here, and that will be for some small n, so just choose n as some large number, like at least 10 or something, whatever. So they are distinct numbers, and both of them are at most n minus 1. And therefore their product will divide n minus 1 factorial. Because in the expression of n minus 1 factorial, these two distinct numbers appear. Right? So they divide n minus 1 factorial, and therefore n divides n minus 1 factorial. Case 2 is when you have equality. P is equal to square root of n. So here we will have n as p square, and we want to show that n divide n minus 1 factorial, that is, we want to show that p square divides p square minus 1 factorial. Now here's the thing, if 2p is less than p square minus 1, which happens very generously, less than equal to p square minus 1, then we are done. Why is it that we are done? Because if 2p is less than p square minus 1, then p times 2p appears in this, if you expand out this factorial, right? If 2p is at most this guy, then when you expand out this factorial, both these numbers will appear, and hence in particular we are in fact showing that 2p square divides n minus 1 factorial. So just think about this. And when does this happen? This happens very, very generously. I think if p is at least 4, this will happen. Right? So 2 4s are 8, and yeah, if p is 3, then maybe we are in trouble. No, even with p is equal to 3, this is fine. P is equal to 2, we are not fine. So if p is at least 3, then we are fine. So at least for large enough n, this argument works. If n is some big enough number, maybe at least 10, this argument works. And for smaller values of n, you can just verify by hand. This is anyway an overestimate also. Alright, so I hope this is clear now. Okay, so let's move on. So let us restate Wilson's theorem in this language of Z mod nz. Recall, what is Z mod nz? Z mod nz is set of all the remainder classes modulo n. And one way to write it is the following. It's nz, 1 plus nz, 2 plus nz, up to n minus 1 plus nz. That's what Z mod nz is. We also write this as the remainder class of 0 modulo n, the remainder class of 1 modulo n, and so on. So that's Z mod nz, and there is an addition and a multiplication defined on it. Let me recall the multiplication. So the multiplication that we discussed is as follows. This is the formal picture. So what does the multiplication do? It consumes two remainder classes and outputs what? Outputs the remainder class of the product of the representatives. Complicated statement, but actually very simple. So this is just an enunciation of the modular arithmetic insofar as multiplication is concerned. What this is saying is that if A is congruent to A prime modulo n and B is congruent to B prime modulo n, then AB is congruent to A prime B prime modulo N. This fact allows us to define this multiplication. This wouldn't be well defined if not for that fact. So all of these things we have seen. The more colloquial way to write this is just as follows. We write this is equal to that. This is how we write it in practice anyway. So that's the product defined on it. And yeah. So Wilson's theorem can now be restated as follows. Wilson's theorem just says that if you multiply the remainder class of 1 with the remainder class of 2 with the remainder class of 3 and so on up to remainder class of p minus 1 where p is a prime, then you get the remainder class of minus 1 modulo p. The remainder class of minus 1 modulo p is same as the remainder class of p minus 1 modulo p. So this is an alternate statement of Wilson's theorem, not really alternate, just the language is different. Okay. So now let's go to some applications or a puzzle. So fix a prime p. Then this number we want to show is not an integer. Before we prove it, let me state a fact. More general fact, if n is any integer at least 2, then the sum is not an integer. So this is obviously more general than what we have written over here. But proving this, in my opinion, requires a little bit more. There is an elementary proof, but you can Google it. We are not going to get into that. To illustrate Wilson's theorem, I think this is the correct thing. There you need to mess around with other things. All right, so let's see. Here is the proof. Suppose not, then this is an integer. Is some integer, call it x. Multiply both sides by p factorial. Or maybe, yeah, I think p factorial is fine. So let's multiply both sides by p factorial. So we will get this, but now note that this is divisible by p, that is divisible by p, that is divisible by p up to the last term, up to the second to last term, except for the last term. So all the things before the last term, they are divisible by p. So maybe I will write it that way to illustrate it better. So, so we get p factorial divided by p minus 1 over here. So what I'm saying is that all of these terms, they are divisible by p. Right? Because there's a glaring p sitting on top. After you cancel out the 2 here, in the expression of p factorial or in the expansion of p factorial, after you cancel out the 2, there is a p sitting over there. Similarly for all of them. So this is divisible by p. The right hand side clearly is divisible by p. So the implication that we draw is that p divides p factorial by p. P divides this much, p divides that guy, so p must divide that guy. But what is that guy? That guy is p minus 1 factorial. Right? But that is false. By Wilson's theorem, that is not true. In fact, you didn't really need Wilson's theorem here because p is relatively prime to everything in the expansion of p minus 1 factorial. But if you use Wilson's theorem, this gives us that p divides minus 1, which is clearly false. So yeah, you didn't really need Wilson's theorem. Here, this argument goes through without Wilson's theorem because this is clearly false by usual properties of GCD. And yeah, so let's see one more application. So this is a nice puzzle. Fix a natural number n, and for each such natural number, define hn as the GCD of n factorial plus 1 and n plus 1 factorial. We are asked, what is the maximum of hn when n is at most 100? right? So think about it. It's not exactly simple or easy, but using Wilson's theorem, this is not that difficult either. So let's see. So note that first thing we note is the following, that this GCD is same as, for trivial reason, these two things are the same simply because this is same as that. So nothing has happened so far, but this is equal to, and here something interesting has happened. Why is this true? Well, these two things are relatively prime. Any two consecutive integers are relatively prime. So these two things are relatively prime, and hence by the dropping property of the GCD that we discussed, that if you're trying to estimate or find out this thing, suppose you're concerned with this thing and you find that A and B are relatively prime, then this is equal to GCD A comma C. So that's what we used. Okay. Right. Now if n plus 1 were composite, if n plus 1 is composite, then as we saw previously in a few slides ago, then n plus 1 divides n factorial. Right? What we showed was if n is composite, then n divides n minus 1 factorial. Exactly the same thing we are using. Instead of n, we have n plus 1. So we have this, and therefore the GCD of n factorial plus 1 and n plus 1 would be 1. Because n plus 1 divides this guy, assuming it is composite, we would have this GCD is 1. So the only interesting or non-trivial GCDs will occur possibly when n plus 1 is prime. And yes, when n plus 1 is prime, this leaves a remainder of 0 modulo n plus 1 this leaves a remainder of minus 1 modulo n plus 1, and therefore this would leave a remainder of 0 modulo n plus 1. Meaning if n plus 1 is a prime, this guy is divisible by n plus 1. So if n plus 1 is a prime, then n plus 1 divides n factorial plus 1 by Wilson's theorem, and therefore we get the GCD is n plus 1. And now it's clear how to maximize this guy. Just choose the largest possible n such that n plus 1 is a prime. Largest possible n in this range such that n plus 1 is a prime. That will give you the maximum possible value. And what is the largest n for which n plus 1 is a prime? Well, 100 is one such number. 100 is that number. 101 is a prime. So if you just take n as 101, you get the GCD is 101. And you cannot go beyond that. Right? Because this thing is of course at most n plus 1. The GCD of something comma n plus 1 is going to be at most n plus 1. So whatever n you substitute, whatever n you choose, you cannot get a GCD of bigger than n plus 1. But if you substitute n as 100, you get GCD as 100 plus 1, namely 101. So that is the best. So the maximum you will achieve is when n is 100, and yeah, so your answer is 101. Okay. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.